Okay. Hello, everyone. I'm David Froelicher. I'm a first-year PhD student at EPFL in Switzerland, and I'm going to present Unlynx, which is a decentralized system for privacy-conscious data sharing. This work has been done under the supervision of Brian Ford and Jean-Pierre Hubot. And one of the main motivations for our data sharing system comes from the medical domain. And with this first graph, we can see that more and more medical data are digitized, with nowadays almost 80% of the medical records that are digitized in the US. And we also all well know that we are collecting more and more data about ourselves, about our health. And one might think that all this medical data that can be processed should help a lot in order to improve medical research and to find new treatments. But this is not really the case, or at least this is not really the case for the example of the cancer. And with this graph, we can see that for the most well-known cancer, the cancer death rate is almost constant since more than 8 years in the US, with two exceptions. So the first one is the lung cancer, but this is probably because of the cigarette. And the second one is the stomach cancer that almost disappeared, probably because of the invention of the fridge. But for the others, it's constant. And we think that one of the reasons for that is that even though we are collecting more and more medical data, these data are really sensitive and really complicated to share, because when you want to share this sensitive data, then you have to follow all the rules and regulations stated by the government. You have to get the patient consent, which requires a lot of paperwork, and it requires a lot of money, and it takes a lot of time. And so it results in companies and medical institutes that are collecting more and more data, but these data are kind of stored in what we can represent as big silos, but are not shared among the different institutes. And so to overcome this issue and to improve the privacy-conscious data sharing in general, we propose Unlynx, which allow queryers to do SQL statistical queries on a set of distributed and independent databases. The queries can be based on Boolean conditions, and the results can be grouped on certain attributes. So we want to propose a new solution while avoiding two issues that we see in most existing data sharing solutions. So we want to avoid to have a single point of failure, which is the case with centralized solutions where one entity is responsible for all the data storage or all the computations. And we want to avoid to be limited in the number of data providers or computation entities in an adversarial model, which is often the case with existing secure multi-party computation. So our new solution should fulfill a set of requirements. And so the first one is that the data should be protected during storage and under computation. So the data confidentiality should be protected under computation and during storage. We want to provide unlinkability for the data providers, which means that no entity can infer information about the data providers by looking at the data under computation. We want to provide differential privacy for the data providers and the individuals storing their data in the data providers. We rely on decentralized trust to avoid to have one single point of failure. And we want to provide correctness and accountability by having ways of verifying all the computations that are done in the system, and by having ways of removing an entity from the system if this entity is misbehaving. So in order to fulfill these requirements, we rely on four main building blocks. The first one is the collective authority, which is a group of servers or computation entities that will collaborate in order to handle all the computations in the system. And they will collaborate in a way such that if at least one server is honest, then all the security and privacy guarantees remain guaranteed. We use the additively homomorphic Elgamal crypto scheme to protect the data during storage and under computations by doing all the computation in the encrypted domain. We use the zero-knowledge proofs of correctness proposed by Kamenisch in order to provide accountability and correctness. And we rely on the verifiable shuffle proposed by Neff in order to provide unlinkability and differential privacy. So in our system model, we assume a set of M servers that form the collective authority and that will handle all the computations in the system. We have a set of N data providers that have their data encrypted and that wants to share their data. And we have a certain number of queryers that can query the system. In the threat model, we assume an any-trust model for the collective authority, which means that as long as one server is honest, then all the security and privacy guarantees remain guaranteed. We assume the data providers to be honest but curious, because we cannot yet provide input validation, so we cannot yet verify that the data that they input as a response to a query are correct data, and we want to avoid them to collude among themselves. And finally, the queryers can be malicious. So now we will go through all the steps that our system executes in order to respond to a query. And so before any query enters the system, the server in the collective authority will each generate their public-private LGAML key pair, and then they will aggregate their public keys in order to create a collective key, a public collective key, which is then used by the data providers in order to encrypt their data. Since the decryption key or the secret key corresponding to this public collective key is the aggregation of all the server's secret keys, as long as one server is honest, then all the then is honest and does not share his private key, then the decryption key cannot be constructed, and all the servers have to collaborate in order to decrypt any data. So then once a querier wants to do a query, so in this case we use a medical example where the querier wants to know the average cholesterol rate for all the people that are between 40 and 50 years old that are Caucasian, and he wants to know the result for men and women. So this query is broadcasted to all the data providers, which will then respond with their encrypted data. So in this case, we have a simple example of a data provider's database where all his data are encrypted with the public collective key. And in this case, the data provider will simply select the column in his database corresponding to the query attributes and send his encrypted data back to the servers. Then, in order to break the link between the data providers and their data, the servers will do a verifiable shuffle protocol. So each server will do this protocol, and this protocol is done collectively. And each server will sequentially shuffle the list of all of the responses and re-randomize or re-encrypt all the ciphertext in the responses. And this is done by using the NAF shuffle, which can be verified by using zero-knowledge proof of correctness. Then, in order for the servers to be able to filter the responses based on the Boolean conditions in the query and to group the responses based on an attribute, the server will run a distributed deterministic tagging protocol, which will allow them to collectively create a deterministic tag from a probabilistic encryption, and that will allow them to compare the responses, filter the responses, and group the responses. So this protocol will be executed on the query attributes and on all the responses sent by the data providers. So this protocol is done collectively by the servers, and each server will sequentially partially decrypt the ciphertext by using its private key and blind the same ciphertext by multiplying it with an ephemeral secret key. So each server will use the ephemeral secret key for one query only, and once all the servers have done these operations, it results in a deterministic tag that only depends on the message and on the ephemeral keys used by the servers. Again, this can be verified by zero-knowledge proofs. And then the remaining responses are collectively aggregated by the servers. And after that, in order to ensure differential privacy, so to avoid that any entity can infer information about one single individual or one single data provider, the servers will run a distributed results obfuscation. So this protocol relies on parameters that are defined in the initialization step. So in the initialization step, the servers agree on some differential privacy parameters. They produce the corresponding distribution curve, and they will quantize this curve in order to create a list of noise values, which is public and non-encrypted, and that will satisfy differential privacy. And so at runtime, one of the servers will start a collective shuffling protocol on this public list of noise values. This will encrypt the list thanks to the re-randomization, which is part of the shuffling process, and this will shuffle the list. And at the end of this process, the server will simply select the first element in the shuffle list and add this element to the query result. Since no entity can know which noise value it is, but they all can verify that it comes from the list of public noise values, this will correspond to an oblivious noise addition, and this will ensure differential privacy for the result. And finally, all these operations have been done encrypted under the public key of the collective authority. And for the querier to be able to decrypt the result, and such that he is the only one able to see this result, we have to switch the query result, which is encrypted under the public collective key, to the same result, but encrypted under the public key of the querier. So this is done by using the key switch protocol, in which each server will sequentially partially decrypt the ciphertext by using its private key and encrypt the same ciphertext by using the public key of the querier. So this will switch the encryption from the public key to the public collective key to the public key of the querier. And all these operations can again be verified by using zero-knowledge proofs. Finally, the querier is able to decrypt the query result by using his secret key. So in terms of performance, we use classic machines as server. These machines have 24 cores, which is important because we can parallelize the operations that are done on the ciphertext. We rely on an elliptic curve that provides 128-bit security. And as default parameters, we use 3 servers with 15,000 responses in total. And the query is done on 1 group by, 1 where, and 10 aggregating attributes. So in this first graph, we can see how the servers will collaborate in order to respond to a query. So they will each independently start the verifiable shuffle and then the distributed deterministic tagging protocol. This can be done independently by the servers. And after that, they have to wait until they are all ready to collectively aggregate the responses, then do the distributed result obfuscation in order to provide differential privacy. And finally, they will do the key switch. So in this graph, we can also observe that the communication cost is the most important cost in our protocol, with more than 70% of the runtime. And we can see that the verifiable shuffle and distributed deterministic tagging protocols are the 2 protocols that takes most of the time. And this is because these protocols are executed on all the responses sent by all the data providers. And these responses have to be processed by all the servers in the collective authority, so they have to be sent through all the servers before they are collectively aggregated. And in the last 2 steps, only the aggregated responses are processed in the system, which reduces the communication cost for these last 2 steps and which reduces the runtime for these last 2 steps. So on the right, we can see that the runtime of our system increases linearly with the amount of data that needs to be processed. We can see that the communication cost is the most important cost. And on the left, we can see that the overhead in order to create and verify all the zero-knowledge proofs for all the operations that are done by all the servers is non-negligible. It increases linearly with the amount of data that needs to be processed. But these parts of the protocol can be done offline, as at runtime, the servers only have to save all the information that are required in order to create the proofs if the proofs are asked by the user. And so this leads to an obvious trade-off where the user can only ask for parts of the proof to have better performance. And so in this case, we use the same query as before with 400,000 responses. And we can see that in the baseline scenario, so if all the proofs are created and verified, the runtime to respond to this query is 24 minutes. This runtime can be reduced if the user chooses to only ask for parts of the proof. So in this case, the security and privacy level is still high because the servers cannot predicate which proofs will be asked, and so they have to behave correctly for all the computations. If the user chooses to trust the server, then he won't ask for the proofs, and then the runtime is reduced to 2.5 minutes. And finally, in the best case in terms of performance, if the data providers have some attributes that are not encrypted in their database because they think that these attributes are less sensitive, then they can already pre-aggregate the responses based on these attributes, which will reduce the amount of data that needs to be sent in the system and processed by all the servers, which will reduce a lot the communication cost in the system, and which will reduce the overall runtime down to 0.4 seconds. So to conclude, we present a system that allows queryers to do SQL statistical queries based on Boolean conditions on a set of distributed databases. This system provides strongest link security, data confidentiality, and we design new protocols in order to ensure to provide distributed differential privacy and to collectively create deterministic tag from probabilistic ciphertext. And finally, the link to the public implementation of our system is available on the bottom right of this slide. Thank you.